power plants, you all know CO2 production is there. In exhaust, we are producing CO2. If forestation is there, there is no issue. But availability of land itself not available for a human being, where the forestation is coming to the picture. So greenhouse effects are coming. So it leads to rise of sea level and reduction of the land availability. So by coal or thermal power plants also, direct by fossil fuel, practically it is not possible to reach our demands, needs. Okay, next move to hydro. Hydroelectrical, very good. So in India, according to the level of melting of Himalayas or the level of height Ganga, where it is coming from Himalaya, Alakananda, Mandakini, Gangotri, Yamunotri. After mixing of these four rivers, we can call as a Ganga. Means the four Himalayas areas are melting and mixing some Haridwar or Rishikesh, I think, Rishikesh. And we are calling Ganga, and the height, Himalaya height, maybe 3 kilometers, sea level from sea level, how much mass of the water is melting, ice is melting, then based on that calculation, the maximum potential of electrical energy generation in India, different river basins, maximum capacity is 1,48,701. Up to now, we installed already 46,322. Maximum 1 lakh is possible. That is for that construction, huge area, catchment area is required. Huge investment cost is required. It is practically not that much possible to utilize entire 1 lakh 48,000. Even though we utilize it also, that is not sufficient to fulfill our needs. Next, Tamil Nadu peoples very well knows regarding wind energy. I think 100% windmills are available in Tamil Nadu. I think windmills, that blades manufacturing, generators, 3-4 companies are available in Tamil Nadu. The total installed capability is 48,565. Now 37,744 megawatt already installed. Okay, one more option, biomass. That is also maximum capacity is 25,000. So only one opportunity is there, that is solar. In any other method, we are unable to generate the needs of, we are unable to fulfill the needs of future electrical utility. So solar only the option. Again, why solar PV is more popular, why solar thermal is not popular, we will discuss later. First, solar is the option. So 87.5% of the solar energy we are using for agriculture, forest and housing industry. These areas 87.5% of solar energy already utilizing. But agriculture, the photosynthesis process maximum conversion efficiency is 2%. So 10% area we are using also, we can produce 8 million megawatt. So 10% also not required. 1% is utilization of solar energy also is more than sufficient for our future needs. So next, once we selected one research area, means at least after our PhD, at least 10 years, 20 years, it has to in limelight. Then we can do some work. Every year we can't select new area. Whatever the efforts we made for attaining the PhD degree, at the time itself, the burning topics we are selecting, then we can continue our research in our teaching field also. So why I selected in solar thermal means this is the main reason. Next, the tool, Exergy tool I selected for that analysis. Before that, whenever we are teaching, we are explaining, we are discussing thermodynamics means 2 words every time we are discussing. One, perpetual motion machine of first kind. Second one is perpetual motion machine of second kind. So perpetual motion machine of first kind means it is a violation of first law of thermodynamics. Energy is conserved. But here without input, we can produce output. That is a statement of perpetual motion machine of first kind. So without input we cannot produce output. The first statement. Second one, perpetual machine of second kind. This one, we cannot construct single reservoir heat engine or 100% efficiency practically not possible in thermodynamics. From heat to low grade energy to high grade energy conversion, 100% efficiency practically not feasible. We are violating this, it's called perpetual motion machine of second kind. So every time we are designing the system or proposing cycle, we kept in our mind energy must be conserved. Even though energy conserved is practically feasible or not, means the conversion efficiency must be less than 100%. Or we want to construct heat engine, at least required 2 reservoirs. Not only second law explained that one, directional feasibility also explained by second law of thermodynamics. A cup of hot coffee does not get hotter in the cool room, no doubt. It will cool in the cool room, but does not get hotter in cool room. Second, by the pedal wheel, we can generate heat. In Joule's experiment, we are doing that one. We are generating heat. But by supply of heat to the pedal wheel, we cannot generate the mechanical energy. Next, electrical resistor also. By supply of the electrical energy through the resistor, we can generate heat. But by supply of heat, we cannot generate the electrical energy. So directional feasibility, energy has quality and quality. So second law analysis can explain the theoretical limits of performance of commonly used all engineering devices. Based on second law, only whatever the analysis we are doing, that analysis only the exergetic analysis, means theoretical feasible analysis. Theoretically, how much efficiency is feasible. In a practical case, we can estimate by exergetic analysis. So already the statement we given, Kelvin-Planck statement means we cannot construct single reservoir heat engine. Next, class A statement, heat cannot flow from low temperature to high temperature unless otherwise we are supplying some work through the pump. By using pump, by external work input, only we can transfer the heat from low temperature to high temperature. And quality of the energy, generally we are increasing the temperature, means the available energy is increasing up to defining the classes inequality. Up to that, what we assumed, if I am increasing temperature, means the quality of the energy is increased, the efficiencies are increasing. But once class S is realized, 1865, whatever the inequality is stated, that is not inequality, it is a property, is called entropy, the molecular disorderness. Here we are increasing the temperature, heat value is increasing, but the molecular disorderness also increasing. This is a reversible case and irreversible case. We are adding S generation. So that's why in power plants you see 1950 boiler pressure is 30 bar at 1951. In 2009, I think 2008, the Reliance Anil Ambani Group first installation of supercritical thermal power plant, the boiler pressure is 221. But boiler temperature is 1951 is only 350 degrees. Now temperature is 580 degrees. Maximum limit is 600 degrees only. The temperature just doubled. The pressure we increased at least 6 to 7 times higher than the 1950s pressure. Why? Because if I am increasing sorry, this temperature difference 800 Kelvin, 2000 kilojoules of energy is available. Sink is 500 Kelvin and 750 Kelvin. If temperature difference is high, the entropy generation is high, 1.5 kilojoules per kg. If temperature difference is low, the entropy generation is very low, 0.2 kilojoules per kg only. So it means less temperature difference will give, it means less temperature difference will give more available energy. That's why olden days majority of the water heaters are biomass based water heaters. Why? Because their biomass combustion, the temperatures will get 400, 500 degrees temperature. The hot water temperature is required 40 or 45 degrees. That much of temperature difference is there. With less, because of that, more we are losing more available energy. That one is replaced in 1980s. MNR, Ministry of New Renewable Energy, introduced subsidy in solar water heaters. In solar water heaters, flat plate collectors are ETC tube collectors. The temperatures here are 50 to 60 degrees. Utilization temperature is 40. So it is easy to, the temperature difference delta T we are reducing means reduction of the entropy generation will take place. Available energy is increasing. So this is the second output of the second law analysis. Then entropy for reversible process, equation of entropy we already derived this one for solids and liquids, and for the non-flow gases, for non-flow process, integral Cv into dt by T plus universal gas constant R into ln V2 by V1, or for flow process Cp into ln T2 by T1 minus R ln P2 by P1 for reversible process. Irreversible process, some more generation we want to add. So finally we reached why we selected second law analysis means realistic outcome based on the theoretical analysis we can achieve. That's why we selected Exergy as a tool. Then what is the Exergy? The useful work potential of given amount of energy at some specified state. What is that specified state? So 1000 degrees of temperature at 5 bar pressure, some energy is there. That is specified state. To the dead state. That state to dead state means that is the environment state. That dead state condition always changing. Area to area is changing. One best example I will give. It may be useful for explanation of students. Suppose student have 10,000 rupees in his hand. He want to pocket money like that. You want to save in different banks. You may move to HDFC Bank, ICICI Bank, SBI Bank, or Grameen Bank. Different banks they are moving, commonly students. So any bank you have 10,000 means they will open your account, no doubt at all. Then after your energy value is 10,000 rupees. But after depositing of the banks, the withdrawal capacity is changing. Suppose HDFC, ICICI Bank, you are open the account means 4,000 something minimum balance is required. So your available money only 6,000. Remaining 4,000 you want to extract means your account want to close. So your available energy means your capacity is 10,000 rupees. Your capability only 6,000 rupees. Suppose you open in the Grameen Bank, the minimum account balance is 100 rupees something. SBI Rural 500, SBI Urban 1,500. So deposit is 10,000 only. Based on the bank condition, withdrawal condition, the capability of the amount withdraw is changed. That capability calculation only Exergy. So Exergy, every time we are giving the Exergy value, it is a defined value at a particular instant. With respect to dead state we are giving. If dead state conditions are changing means the Exergy values are changing. That's why I analysis on thermal power plant. Same thermal power plant, they changed the location, the operating temperatures and pressures are same, but the dead stage conditions are changed. That condition also the values are changing. So Exergy means, best example, Exergy, it's a combination of energy and entropy, or energy equal to, it's the capacity of to do work, Exergy capability of to do work, this one capacity of to do work, this one capability of to do work. Energy is non-available system. That energy, how we are calculating is important. That non-availability is by changing the process we can achieve or not. That testing only is required. That's why we are doing exergetic analysis for all thermal systems. For changing process, different process, how we can reduce the unavailability. These are the efficiency equations. These all the equations are there. So energy is conserved, entropy is generated, exergy always destroyed. For high grade conversion of the energy, the unavailability is negligible, like potential energy to the mechanical energy. For non-flow equation, steady flow energy equation, for non-flow process, available energy, because non-flow process, internal energy we are considering, internal energy of current state minus internal energy of dead state minus T naught into entropy of current state minus entropy of dead state. If you consider the piston losses, piston work done, then we are subtracting P naught into V2 minus V1. For steady flow process, majority we are using for power plants, steady flow process uh, equation, this basic equation with mass, some energy, and energy is entering. For entering of the energy, it is performing some work on the system. So flow work, internal energy plus PV, enthalpy, and having kinetic energy, having potential energy. If you supplied heat, from the system, again some mass is leaving with the enthalpy, with the kinetic energy, potential energy. If by leaving, if they performed some work, then we are adding work. This is the steady flow energy equation for based on first law of thermodynamics. Same Exergy equation also same thing for availability of state 1 to state 2. The difference only the maximum useful work. This basic equation we are using for analysis of power plants. So you see the Exergy in we calculated. Suppose solar energy available at 5400 Kelvin temperature. Then it reached to the area, the earth, and we are consuming. At that in different process, I am consuming. Some loss is taking place. By this loss, maybe we can avoid by changing the process. That we will cross verify with while in our analysis we can cross verify how we can change the reduce the losses. Second one is Exergy wastage. Wastage to the hello. Exergy wastage to the ambient. This one we are unavoidable. Why? Because ambient condition is also dead state condition. Our Exergy loss also dead state condition. This is unavoidable. This one is avoidable. How we can avoid it? We can explain. These are the equations. These are everything available in our papers. Maybe we can search it in Exergy, maybe B. Siva Reddy or SC Kaushik, like that. You will get the publications. Now, I think why we selected Exergy tool and why we selected solar. Move to today's topic, exergetic analysis of solar thermal power plant. Here we selected 50 megawatt parabolic trough solar thermal power plant. This one in 2009 I started analysis. I think 2010 or 11 I published the data. At that time in India there is no power plant. So from published data only we selected the parameters, design parameters. And for Indian atmosphere, from NRL, National Renewable Energy Laboratories, last 4 years solar data is available. Anyone can download. By using that data only, this model, we analyzed the model. If we place data, full high solar intensity area Jodhpur and low solar intensity area Delhi, because at the time I'm in North India, so I selected the two areas. First of all, generally in parabolic trough we are calling collector means it is a combination of modules. You see, this is the modules, 12 modules. One collector means it is a combination of 12 modules. One module width we selected means commercially available width is a 5.76 meters. If you went that solar energy center at Gurgaon, now it is this type of power plant is available, not 50 megawatt, I think 1 megawatt or 2 megawatt power plant. So the width is 5.7 meters. Length of the each module is 12 meters. The effective length is 11.9 meters. Remaining is left for joining joints, for creating joints. So 144 meters length, one collector length of parabolic trough means 144 meters length. And so for the 144 meters length, only one tracker tracking is one tracker is sufficient. Like that, collectors we are connecting based on the solar intensity in series and parallel. Once the series is completed, desired temperature is 500 Kelvin. So up to 500 Kelvin, but at a defined mass flow rate, how many collectors we want to connect in series. Then after collectors are connected to the parallel conditions. Then this collector system is connected to the hot tank and cold tank. From the hot tank, it is moved to the boiler, and from the boiler exhaust, it will come to the cold tank. This is the thermal power, general thermal power plant. You see, reheat, regenerated, superheated, Rankine cycle thermal power plant. Not supercritical, superheated, reheat, regenerated. The regenerated operation, two high pressure regenerators. One is open regenerator, deaerator, for deaerator purpose, open regenerator, and three low pressure regenerators. And reheating, after a high pressure turbine exhaust, again we are reheating the steam for expansion, further expansion of low pressure turbine, reduction of the moisture content in the end stage of the turbine blades. This is the single one. Receiver, evacuated tube. These all are data collected, and this is the TS diagram of the 50 megawatt parabolic trough solar thermal power plant. Then the basic equation I already mentioned, steady flow energy equation only we are using for determination of the power plants. Here, the main beauty of the analysis, we considered reduction of the load, the reduction of the performance efficiency also we considered from 1958 publication, the high pressure, low pressure turbine efficiency, how it will reduce, and pump efficiency, how it will reduce, and generator efficiency, how it will vary with the load. Means realistic output, our target. By theoretical analysis, we want to achieve the realistic performance efficiency. Then this is the heat from the source of solar beam radiation. We all know for concentrated collectors we are using only beam radiation. Flat plate collectors we are using diffused radiation. And area of the collector, number of collectors, number of rows, number of modules per collector. Generally we selected for these 12 modules. Universally accepted that one. Majority of the power plants contains 12 modules only. And the cosine losses. Then exergetic value, this exergetic input value of the source. This one Petla 1964 he published the equation. We use that one. Then how much is absorbed, reflectivity, transferability, absorbability, and end losses. Everything we considered. So basic model, this one I published same total paper I published in I think Energy Journal. you can cross verify. So where we got the design considerations means at the time 2009 published data we considered absorber tube outer diameter is 70 mm diameter, absorber tube inner diameter 65 mm, glass envelope is 115 mm, and glass envelope inside diameter 105 means thickness of the glass is 6 mm thickness of the glass. And for the Jodhpur, I have mentioned high solar beam radiation 870 watt per meter square. So the number of collectors we selected 4 per series. Same system we installed in Delhi means the number of collectors we increased it to 65 because the solar beam radiation, average solar beam radiation availability is 620 only. And the width of the module I mentioned already 5.76. The length of every module 12.27, but mirror length only 11.9. The ambient temperature we selected 304, and the incident angle, focal length, and the focal length is 1.71. Hydraulic drive, that tracking system is hydraulic drive. Next, mirror efficiency, glass transmissibility, everything the realistic manner we consider. Next, the power plant operating parameters you can see. The extraction, each end of the first stage, second stage, third stage, 2 high pressure regeneration, 1 open feed water heater, and 3 low pressure regenerations is there. For extraction, where it is extracting the percentage at 0.5 into high pressure, and that at the end one stage is completing. After the stage only we can extract the steam. Next, after the next stage of the extraction, like that the extraction percentage of the high pressure and high pressure, the extraction stages are there. Giving any design power plants, you open the design data book of power plants, you will get, because exactly pressure they will not give. If I change it high pressure means the extraction pressure is also changing. So that is the only the collected data. I am not did anything. Whatever the 2009 published data is there from the journal, I developed the model and analyzed the exergetic analysis and energetic analysis. So collector receiver area only low exergetic efficiency, and the overall plant efficiency, the energetic efficiency is 24%. The exergetic efficiency is 25.81. Generally, exergetic efficiency we want to get less value, but according to Petla equation, solar energy at the source is high value 5400 Kelvin, but it come to the earth the value is reducing. Because of that only light variation of the exergetic value is coming, but major then whatever the model, why? Because practically means there is no validation, but theoretically we are doing first model validation is required. Our model compared to the published data, almost we got nearer values. So then we want to do modifications. What are the modifications we can takes place? Already I mentioned we can't increase the temperature. If you increase the temperature, the available value is reducing. So we can increase the pressure. You are capable to increase the high pressure, allowable increasing of the high pressure, possible allowable increasing of the high pressure we calculated. How, what is the limitation means? The end stages of the turbine blades, what the dryness fraction. That is our target. More than 9 dryness fraction we want to maintain. Wilson line, we are calling Wilson line in power plants. More than that dryness fraction, if you are maintaining means damage of the turbine blades we can eliminate. So with that target, we analyzed different sink temperatures, the high pressure turbine high pressure we are increasing, how the energy is efficiency is increasing, and the dryness fraction reduction, how it is reducing. So the optimum turbine pressure we can achieve earlier condition, the published data is 90 bar pressure. Now up to 105 bar pressure we can increase without changing any operating parameters. Then we extracted the operating parameters, each stage of the extraction process, each stage operating parameters, and we determine the entropy and exergy value and energy value. Then we calculated the overall efficiency of the power plant. The overall efficiency of the power plant we got 26.2. The energetic efficiency is 24.75. The earlier condition, the model is 24 and 25.81. So almost 1.2, 1.4 percentage of the efficiency we increased by enhancing the inlet pressure. This enhanced efficiency cycle, power plant cycle, if I run in the location of Jodhpur, this is the Jodhpur solar radiation variation of the from morning to evening, so 8 a.m. to around 8 p.m. 8 a.m. to 8 p.m. but maximum 5 to 6 p.m. is more than sufficient. So how the solar radiation is varying per month, you can see in the month of August less solar radiation we are getting. The peak solar radiation in the month of February we are getting. Generally we are assuming high solar intensity will get in summer, but in a general case high solar intensity will get in winter case, but length of the solar day is less in winter. Why we are getting high solar intensity in winter means the condensation of the particulates, the polluted particulates will take place in winter. So clear sky condition will occur in noon time. So solar constant is not changing. 1353 watt per meter square of the beam radiation is coming from the sun to earth. If clear sky, zero pollution, at that condition we can get the highest beam radiation. But that highest beam radiation possibility only available at Jodhpur. You can cross verify in NRL website the solar radiation data. Next, the wind velocities, the dry bulb temperatures, how the dry bulb temperatures are changing entire day. Next, Delhi. Delhi also like that. You can see in Delhi in November we are getting the peak process, peak solar radiation. There February we got the peak solar radiation. Here November we got the peak solar radiation, and least in August, both cases, because in monsoon condition, August least due to high cloudy condition, least beam radiation. These all values are beam radiation, not global radiation. So beam radiation availability in August is very less. Then monthly average wind speed. In Jodhpur, the availability of the collectors are reduced for same 50 megawatt production, but the drawback of the Jodhpur is wind velocity is high. So the structural cost of the collector is increasing in Jodhpur compared to Delhi. So Delhi wind velocities are very low compared to Jodhpur. Jodhpur wind velocities are high. Then after considering cosine losses, what is the end beam radiation? Why? Because we are doing single axis tracking for parabolic trough. That's why we want to consider the cosine losses for Delhi also. Then efficiency variation of the high pressure turbine, low pressure turbine, and boiler feed water pumps and generators and motors. What is the efficiency variation with respect to load? Load means the mass flow rate of the air, the circulating fluid. We are changing. So load will change according to load. Variation of the efficiencies we considered. Then we calculated entire year the efficiency variation of the parabolic trough, the energetic efficiency and exergetic efficiency. In December, you see very low. Next December, November, and October. The high we are maintaining in June. June, April, June, and May. High efficiencies we are achieving for Jodhpur. For total plant efficiency also calculated. This is the total plant efficiency. Compared to coming to the Delhi, Delhi also in April, next June, May. April, May, June, these 3 months, the length of the day is high and overall efficiency is also high in both conditions. Next, the electrical energy generation capacity. These all are theoretical analysis. The electrical energy generation capacity for month wise, January, February, like that month wise, April, May, June, March, April, May, June. These 4 months we are getting high electrical energy generation units. Coming to the here also April. In both case, April we are getting the high number of means length of day is high and the solar radiation also at a design value means Delhi means 650 watt per meter square and Jodhpur means more than 850 watt per meter square. So that's why in April we are getting high electrical units we are generating. So the comparison of Jodhpur and Delhi, the efficiencies, variation of the efficiencies, the year-round efficiency, designed efficiency of the system, whatever the modified parabolic trough system, 25%, 26, 20 exergetic efficiency is 26, energy 25. But for year-round running, the efficiency is reducing. Overall efficiency of the year-round plant is reducing because in August, September, the operating temperatures are reducing. But average overall year-round performance of the system is this one. And total land area requirement. For the same 50 megawatt power plant I want to install at Jodhpur, 80 hectares of land is required. For same power plant I want to install at Delhi, same capacity 550 megawatt, the land area requirement is high, 120 hectares of land. So efficiency, number of units generated we calculated and land area requirement. Next, it will not complete, any analysis will not complete if we are not publishing the economic analysis. Unit generation cost is important. Without unit generation cost, we are publishing data means there is no use. Even though your efficiencies are good, the unit generation cost is going to 20 rupees or 30 rupees, so no one is not ready to accept your analysis. So that is main important. Then we did economic analysis of solar power plant. Here we calculated the unit generation cost. This is the CRF. CRF means capital recovery factor. This one proposed by Kandapal, IIT Delhi professor in 2003. This I interest rate into 1 plus interest rate whole power number of life of the plant divided by 1 plus I whole power n minus 1. This is the capital recovery factor. And investment cost, capital investment, operation maintenance investment, fuel investment divided by the how much electrical units are generated. Then you will get the unit generation cost. Based on the CRF only, this unit generation cost is increasing. Whatever the money we are borrowed, the interest rates are high, then unit generation cost will increase. Our life of plant is low, then also unit generation cost is increasing. So here this one system advisory model. This is also NREL website. One tool is there. From the tool we can extract the data because site improvement per meter square how much cost universally we are giving. Our cost of the collector, general cost of the collector, storage system, the power plant cost. These values I extracted from the system advisory model. It is also available at National Renewable Energy Laboratories. Then I know the site area, then Jodhpur and Delhi, what is the cost. Indirect cost also. Engineering, procurement, construction cost, generally the limit is 11% of direct cost. This is our power plant, Indian power plant, the benchmark cost analysis, 11% of direct cost. And project, land and miscellaneous costs, generally 2% of direct cost. Then this is the total direct and indirect cost of power plant installation for Jodhpur and Delhi. Next, operation and maintenance cost. These also fixed costs and variable cost by the generation. The fixed cost is 1 kilowatt hour means 3,500 rupees kilowatt per year. 3,500 rupees we want to spend that operation and maintenance cost. And variable cost by the generation, the 150 rupees per megawatt hour. These two are also fixed costs. So this operation and maintenance cost we calculated. Then the total megawatt operation and maintenance cost this much. Then unit cost is the unit generation cost we calculated. That one Delhi 14 rupees 76 paise for Delhi at 10% interest rate and 30 years life. For Jodhpur 11.7 rupees, 10% interest rate and life plant is 30 years. And I am not considered any government subsidies or import duty exemptions. I am not considered anything. The realistic manner, if anyone construct the 50 megawatt plant, then what is the electrical energy generation cost? This one also published in Renewable Energy Sustainable Reviews journal. This paper also published, economic analysis also. So unit cost, how it is varying with respect to interest rate, I already mentioned. Interest rate and capital cost we are increasing with the load factor. If 100% load it is running, 90% load, 80% load, 70% load, operation maintenance cost, capital cost. So finally the conclusions are, I already mentioned, at 10% interest rate, a normal acceptable rate, and 30 years lifetime, parabolic trough unit generation cost if we installed in Jodhpur is 11 rupees 70 paise and in Delhi is 14.76. But all are knows at present, I think in 2021, I analysis at the time of 2009, solar PV power plants unit generation cost is 14 rupees. Indian government ready to purchase 14 rupees cost. Later it reduced to 7 rupees. Now the solar PV power plants unit generation purchase 2 rupees 65 something. Drastically reduced that one. At that time we compared with the solar PV also in 2009, not now. Then same method, there is one solar concentrated systems, 3 types: parabolic trough, parabolic dish, and central power tower. Central power tower is nothing but is a big dish, splitted dish. That's all. In long we are seeing it's a parabolic dish only, point concentrated parabolic dish only. Central power tower also. Why it's called heliostat plates. One reflector area is 10 meter by 10 meter. With this, all reflectors are maintaining dual axis tracking only. And at the center receiver is there. Only one advantage in parabolic trough, heat transfer fluid is rotating entire solar field. So more pumping losses are there. The circulating pump losses are high because entire solar field line contact, entire solar field fluid has to rotate. But in central power tower plant, in a central receiver is there, in the receiver itself power plant is there, there is no rotation of the receiver. This is main pumping losses we can eliminate, but this reflection losses are more high because whatever the beam radiation is coming, again it want to reflect to half kilometer or 1 kilometer height. Again reflected beam diffusion also will take place. This is a major drawback. In India the central power tower systems are failure systems. one system is installed at Solar Energy Center. That is also not working. Why? Because already estimated beam radiation 20 to 30% reduction of estimated beam radiation we are getting in India. Hello? And that 20 to 30% is reduced that beam radiation again reflect means further reduction is taking place. But we comparison purpose we analyzed the system. If 50 megawatt system we run, I think same Jodhpur and Delhi, the land area requirements are increasing drastically compared to parabolic trough, but overall plant efficiency is increasing and the unit generation cost is reducing. That unit generation cost is reducing. Delhi 12 rupees and Jodhpur 10.09. I fixed the interest rate and number of life of the plant. Then parabolic dish system. Why? Because IOCL in India only one organization is working on parabolic dish stirling engine based power plants. 25 kilowatt system, single unit capable to run 25 kilowatt. IOCL is doing major research on the engine and reflectors and structure, also structural resistance, everything they are working with associated with IIT Bombay and some other R&D organizations also. So in that condition, 25 kilowatt parabolic dish we are connecting series and parallel for achievement of 50 megawatt. Because for comparison of the unit cost generation and land area, this is the land area requirement. The unit generation cost is very low compared to parabolic trough. Jodhpur is 8.76 and Delhi is 11.06. So the final conclusions by the analysis of parabolic trough, central power tower and parabolic dish. Unit generation cost parabolic dish is very low and the land area requirements also moderate in parabolic dish in India especially, not overall. And the installation cost is too high, 21 to 28 crores parabolic trough, central power tower 24 to 29 crores and parabolic dish 14 to 16 crores. That's why I think IOCL major concentrate on parabolic dish. So by this analysis we concluded solar alone is not practically feasible because the unit generation cost is too high. Then what we can do? If solar is my target to utilize the solar energy for generation of power, but solar energy, solar alone means it is consuming more land area. Second, the efficiencies are low and the investment cost of the power plant is high. So no one will come forward of our proposal. Then we cross-verified some more analysis. That one, if solar aided is possible, for I already at the starting of the lecture, one slide I shown 60% of the total power generation only solar thermal power plants only. So this is a critical thermal power plant, supercritical thermal power plant schematic view. So here 4 high pressure steam extractions are there for regeneration process, 4 low pressure and 1 open feed water heater is there. This is also high pressure extraction only, deaerator. So while we are extracting the steam for preheating of the water, reduction of the delta T in the boiler, because temperature difference we are reducing the entropy generation. That's why in boiler feed water, what is our target? It reaches to the saturation liquid temperature. Then the temperature, without changing temperature, it will move to the saturation vapor and move to the superheated condition. That is our target. So for that reason, what we are doing, regeneration process for feed water heating. Instead of this extraction of the steam, the same steam we can expand in the turbine. By using solar energy, we can substitute, by using solar energy, we can substitute these feed water heaters. Then we can enhance the capacity of the power plant. That is our motto. enhance the capacity of the power plant. But one more doubt it will come into picture. Sir, the turbine is designed after 4 stages, the mass of reduction is there. Next 6 stages, again mass of reduction is there. Again 10 stages, mass of reduction is there. Now you are expanding entire mass of the steam. The constant mass of the steam means the turbine blades may damage. Like that, one question mark will come into the picture. But factor of safety is there. Any power plant, any turbine design, if all extractions, steam extractions are failed, at that condition also turbine has to run. That is the first factor of safety consideration. Maybe 1.2 or 1.5 according to mass of extraction. So there is no issue substituting this one. And also this is one we are not doing 24 hours. Solar substitution means 6 to 8 hours only. Then after again the power plant will run their own manner. So it will not affect the life of turbines. First thing. So this is our proposal. For a proposal, direct we are giving that proposal means no one will accept that one. Then we did exergetic analysis of the thermal power plant. This source solid fuels potash textbook I considered 1984. That calorific value, higher calorific value and lower calorific. In the coal, two types of the calorific value is there, higher and lower. If sulfur content is not there in the coal, then we are considering the higher calorific value. If sulfur content is available in the coal, then we are considering lower calorific value. Why? Because sulfur condensation will take place if the exhaust gas temperature reducing to less than 160 degrees. If it is more than 160 degrees exhaust gas temperature means condensation of the moisture in the flue gases is not possible. So that energy we are not gaining. That's why we are considering lower calorific value. If sulfur free coal means the temperatures, exhaust gas temperatures 80 to 90 degrees. So condensation of the moisture of the exhaust gas we can take place. That energy also we can use for boiler feed water heating. That's why we are considering higher calorific value. Then we analyzed the entire power plant. This is supercritical thermal power plant. Then the energetic efficiency we got 43%, exergetic efficiency 42%. The energetic power loss more in boiler because high temperature difference wherever it is available, then more losses will take place. Energy exergetic losses will take place in the boiler. More entropy generation is there. But energetic efficiency losses in condenser, we are assuming more loss in condenser, but it is nearer to dead state. It is not recoverable losses. But in boiler, recoverable losses. If you are changing the process, see the by energetic analysis, condenser is playing more losses. In exergetic analysis, we can visualize boiler losses is high. So from this conclusion, I want to enhance the capacity of the power plant. Instead of increasing the input to the boiler, some other manner we want to consider that some other manner only replacement of the feed water heaters by solar water heaters and solar concentrators. Maybe the operating temperature 250 to 350 is more than sufficient. The substitute of high pressure regenerators maybe 250 to 300. Low pressure regenerator 150 to 200. It is easy to substitute by the solar collector systems. It may be parabolic system, it may be heliostat system, or it may be not heliostat, parabolic dish system or parabolic trough system. We can substitute. Then we calculated if we replace low pressure feed water heaters by solar aided, how much net efficiency reduction. This is without solar aided. The efficiency of the plant is 43.48. But replacing of the low pressure heaters, the efficiency is reduced to 38. If replacing of low pressure and high pressure, the efficiency is reduced to 35.75. Efficiency is reduced because regeneration process is one of the best process efficiency enhancement of power plants. But you see this efficiency is much more higher than the solar alone thermal power plants. Solar alone thermal power plant efficiency maximum 25%. Per year round we are working means 23, 22, 20 only we are getting. but here the efficiency we are getting 35%. So this is one advantage, is higher than the solar alone, and there is no extra power plant construction, and just concentrated collectors land area is more than sufficient. And we are enhancing the capacity, net capacity enhancement, 600 megawatt power plant, we can capacity enhance to 130 extra. 130 megawatt, we can enhance the capacity of the existed power plant by solar aided option. Okay, so these are the conclusions. Yes. So at the end, what we concluded means, first we selected solar. Why we selected means solar is best. In future there is no energy source for fulfill the needs of human being. Second, solar thermal power plant we selected. Why? Because we are mechanical engineers. Tool we selected Exergy for the analysis. But solar alone practicality is very less, because cost of investment is high and efficiencies are low. That's why. But as a mechanical engineer, mechanical related solution we want to conclude. That's why we selected solar aided option, existed thermal power plant, replacement of the regeneration process. We can achieve the efficiency more than solar alone. Solar alone maximum 20 to 25% we are getting. Here we can achieve up to 35%. And the generation capacity also, each plant we can enhance more than 150 megawatt generation capacity. High generation capacity enhancement also is possible. So with this I am concluding my lecture, and some of the lectures given by me, that mechanical engineer opportunities, because at present we are facing so much of problems. Students are not interested to join mechanical engineer. They don't know the importance of mechanical engineer. The only one engineer can give solution of all types of the fields. So I placed in YouTube my lecture on mechanical engineering opportunities, and NBA accreditation also. For the NBA accreditation also, how we are performing, and for mechanical, especially internships are important. So what are the important of internship? Like that, some lectures are there in my YouTube channel. So you may utilize that opportunity. You can visit the YouTube channel.